So in this video what we're going to do is look at how, when we've hydrolyzed a protein, we could identify which amino acids were present. And the easiest way to do this is to separate the products of hydrolysis by thin layer chromatography. So we've already taken our beaker with our polypeptide in and we've hydrolyzed it. We've now got a beaker with a mixture of amino acids in it, and we're going to separate those amino acids. So different amino acids have different side chains, and so they will interact differently with the stationary phase and the mobile phase of our TLC. Since they're colourless, we will need to be able to identify them in some way, and the chemical we use is a chemical called ninhydrin, and it's going to turn purple wherever our amino acid spots are. Okay, so remember that TLC, thin layer chromatography, works because each of the components of our mixture is going to have a different balance between how much it likes to dissolve in the moving phase and how much it will be retained by the stationary phase. So as it's moving up that plate, some of them will grab onto the stationary phase and stay where they are, and some of them will prefer to be dissolved in the solvent for longer, and so they'll move further. So a protein was hydrolyzed, and the amino acids that it produced were analysed by TLC. So the spot of the hydrolysis mixture was placed at the bottom here. This is where we put the spot. So we put our product from hydrolysis here, and then we ran the plate. This is what's called our solvent front. This is where the solvent ran to. And we've found that we've got 3 spots when we've developed it in ninhydrin. So we've got 3 spots, and we can use the table of data of RF values to calculate or figure out which amino acids were present. So remember that RF is the distance moved by our component of our mixture, by our spot, from that starting point, divided by the distance moved by the solvent. So pause the video, get a ruler out and measure the distance between the line at the bottom and the line at the top. That would be the distance moved by the solvent. So you want to get your ruler and line it up with the bottom line and the top line. Now, your numbers won't be the same as that because you're using it in your pack, but line it up and measure it, and then you want to line it from that spot at the bottom, and you want to line it up to the first spot and measure that distance as well. It doesn't matter which units you use, as long as you're consistent. So if you go in millimetres, everything's in millimetres. If you go in centimetres, everything's in centimetres. Because it's a fraction, as long as they're the same units, that ratio will be the same. So the first spot, you should have measured, and if you measured these correctly, let me just get rid of that ruler. Just get rid of that. If you measured this correctly, you will have seen that the distance between the solvent front and the starting line was about 6.2 centimetres, and this spot moved 1.5, and this one was 2.4 from the very bottom line, and then all the way to the top one was about 3.8. So you can work out A, B, C, 1.5 over 6.2, which is 0.24. So it was aspartic acid. And similarly, you would hopefully have found out that B had a value, an RF value of 0.38. So alanine, and C had an RF value of 0.61. So valine. sometimes, because amino acids are very similar structures to one another, they will have very similar RF values in a particular solvent. And if that's the case, we can actually do something called two-dimensional thin layer chromatography, and that will allow us further separation. So we're going to use a square plate, and we're going to start by spotting in the bottom left-hand corner and running the plate in the usual way. So we run it, and these spots are going to separate off in this direction. And we draw on our solvent front, and we can measure the RF values. And we've got our separated spots. But we notice that actually it's kind of a bit of a blob. We're not sure, is that really 3 spots? Is it 2 spots? We're not 100% sure. So what we do next is we take our plate and we turn it 90 degrees. So we've taken this plate and we've rotated it through 90 degrees this way, so that now the spots are lying along the bottom. And we're going to run it again. So we're going to run it this way now, in a different solvent. So we're taking something that separates these slightly differently. I'm going to run it again. And when we run it again, our spots separate. So we started off down here with our mixture, and now we've got 5 separate spots. And you can get 2 RF values and compare those to the booklets, data booklets, and you will have a greater confidence in identifying your amino acid. So two-dimensional TLC just gives us that ability to be more precise in our identification.